So ever since I started doing circuit design, I've really wanted to make a board like this, and it's been a good few years since I started, but I finally felt that I had the skills to make a board that can do this, including the microcontroller and all the code involved. And then I had a project-based class for my master's where I had to make a board anyways, so I figured the stars had kind of aligned, and here it is. This is probably the last audio LED board I'm going to make. I'm very happy with it. I think it's pretty much turned out exactly how I'd like it. And yeah, this video is going to be about how I made this. I'm going to go over the schematic and the layout, and then we're going to show some test signals, show some music with it. So stick around. I think it's a really fun board. It's all going to be open source. You can order this board fully stuffed and assembled from JLCPCB. It came out about $80 per fully assembled board. So if you're ordering the minimum quantity of 5, that's like a $400 order. But you could just get 2 of them stuffed. I think that's an option. Maybe that would be cheaper. But anyways, I just figured it's I put enough work into this. It's worth talking about. I hope you guys enjoy it. Thanks.
All right, so just looking at the schematic, I did this board in KiCAD, like I do all my project boards. And I've split it up. There's a page for the microcontroller, there's a schematic page for the analog stuff that processes audio, and a page for the LEDs, which is just, 512 LEDs. Not too exciting, but I'll walk through it. So going to the microcontroller first. So you can see I've got it split up here in little boxes. I'll start it here with the power coming in. I used a couple different options to power it because I know, I guess I just wanted to make sure one of them would be robust enough. I'm specifically thinking about mechanical robustness in this case. This is a pretty big thing. I want to hang it on the wall. So I want to make sure that whatever connector I use can stand the test of time, stand wear and tear. I used a USB-C. That's what I've been using to program it and to power it. There's a neat little trick I didn't know about that it's kind of like the simplest version of power delivery for USB-C. If you just hang a couple of 5K resistors off of the communication channels on a USB-C connector, you can get up to 3 amps at 5 volts, which is enough for this board unless you drive it really, really hard, really bright with the LEDs, which I didn't intend to do. I'm actually running them at like 2% of their total brightness, and it looks pretty bright. Anyhow, then it goes in, there's a simple linear regulator for the microcontroller to get 3.3 volts. I've also got a barrel jack that comes in with 5 volts. This is the most mechanically robust option, and it might be the one I end up using in the future to actually power it when it's hung up on the wall. The USB-C connector seems pretty robust, but a barrel jack is like large through-hole soldered in tabs, not going anywhere. It could certainly hold its own weight. So that might be the option I go with long term. Although it is fun to be able to just plug it into like a laptop charger or something. And then there's just headers for 3.3 volts and 5 volts. Never had to use those, but they're there. Yeah, I've got a button. The board does more than one thing. So the first state that it wakes up in, state 0, it's listening through the microphone and displaying the FFT of the audio it hears. If you click the button, it'll go to the next state, and that'll display on these LEDs. And that second state is, as it stands right now, it's doing Conway's Game of Life. The third state is taking audio in from a 3.5 millimeter headphone jack and doing the FFT and displaying it from there. You get a much better signal to noise ratio there, of course, because you don't care about the ambient noise in the environment. So if you use a splitter or something coming off from your speakers and you're plugging, from your media device into your speakers with one end of the splitters and the other one goes into this, then that would be another way you could drive this board. Here's the RP2040. It's a really basic layout. There's not much to talk about here. Bypass capacitors. We've got a pull-up resistor on run. So this is something, I forget which one it is. Normally when you use a Raspberry Pi Pico and you want to reset it, to program it, you have to unplug it from your USB connector, hold the button on the board, and then plug it in. That's really annoying. It's bad for the wear and tear of the USB connector, of course. I don't understand why they did that on the Pi Pico boards, but here there's both buttons. I think this one actually is the one that puts it in reset mode. So you like hold this one down and then hold this one down and then release this one and then release this one, which sounds hard, but it becomes very easy with muscle memory. Um, Here's the USB differential pair coming in to program it and stuff. I did also break out the serial wire debug header, but I never ended up needing to use it. I don't know. I was using print statements to debug, and that worked fine. I'm kind of an amateur with the embedded software. Um, 12 megahertz crystal. Nothing too exciting to say about it. There's a 1K, what's it called, a loading resistor, pulling resistor, or something to dampen the loop here. And you can see I've got some labels here describing where different signals are going. Audio toggle, that's to toggle between the microphone input and the line input from the 3.5 millimeter headphone jack. ADC0, this one's the microphone. Actually, this is either audio input because you toggle it from here. SPI to control. In the analog loop, I have a variable gain amplifier thing. So it gives you the option to change the actual analog gain going into the ADC here. Here I have the pin that controls the WS2812, the neopixel LED array. I have a 0 ohm resistor here because I don't know what compelled me to do this, to use an ESP32 C3 Mini as an alternate microcontroller. Uh, this was like a total scope creep thing. I never used this, but if you wanted to, the point is you could hook it up here. You can go remove that 0 ohm resistor that controls the LED array from the Raspberry Pi RP2040. You could solder this solder jumper closed, and all of a sudden you could pop in an ESP32 and you could hook it up to the internet and use it to display whatever images or videos or whatever you'd like, and just use it as a big 16 by 32 LED array. Um, there's a lot of 16 by 32 LED arrays or other dimension LED arrays out there already that use WS2812s, but they're all just the LED array, right? And you've got solder pads somewhere. So if you wanted to put something up in your house somewhere as a display, you'd need to have all these wires flying around. You need to get power to it somehow. I think kind of the nice thing about this board, even if you weren't going to use it for all the audio processing and stuff that I've already written, is that it's all in one. It's just this single PCB. You can have your power distribution and your microcontroller. It's a very tidy solution. You don't necessarily need to put it in a box to hide all the, bodgy wires hanging around there. So that's the idea there. You could pop this in and have a bunch of extra functionality if you were so inclined. I'm not really good at programming ESP32s yet, so you know, I can't even say for sure that it works, but I would wager it does. Anyways, moving on to the analog section here. Big picture, what we have is audio comes in. It has variable gain that can be controlled by the RP2040, and then it has a filter, an anti-aliasing filter, so that when you're processing the audio on the RP2040, you can't get anything above 20 kilohertz. So I'll zoom in here. Here is the input from the headphone jack, left and right. They come in. They're capacitively coupled in, and then they're set to half of the supply voltage. There's an analog switch here. That's what allows you to choose between the audio jack signal or the microphone signal. This is a little MEMS microphone. These are really great. They have an amplifier in the chip, or on the tiny PCB that is the MEMS microphone. So they come out, compared to like condenser microphones or something, they have a very low output impedance, so they're much less susceptible to noise and stuff like that. They make life a lot easier as far as what you have to do. You have a decent amplitude, well-driven signal coming out of this already. Also capacitively coupled, and also you can see what I did here. I split the supply here, and then I dropped 100K resistors to set the bias point for these three lines. I thought it was kind of a fun trick. Then it's coming in here. This analog switch is controlled by that audio toggle pin from the RP2040. So this is how you would toggle, I want to listen to the microphone versus I want to listen to the audio jack coming in. You can see I've got some test points around. The microphone goes through one extra amplification stage because it has a pretty low amplitude. Max I could imagine, even if you're like blasting music right next to it, is like 50 millivolts peak to peak, whereas the line could be like a volt peak to peak coming in. So this way we get them to about the same level at this point, because this switch A2 goes up here, comes into there. So if you switch the microphone in or you have the line in, you can expect a similar range of amplitudes of your audio signal at this point. Then it's coming in here. This looks pretty funny. I just wanted to give myself a spot to kind of take this out if I didn't need it. This is a digital potentiometer that I use to control the gain. It's acting as an inverting amplifier for the audio signal. This way, you get 256 taps on this potentiometer, and you can control the gain in 256 levels, basically. You have 1K coming out, either through here or through these guys. And then this digital potentiometer lets you adjust the gain using SPI from the microcontroller. So you're able to get a pretty wide range of amplitudes, and it's biased to half the supply in the same way that those other ones are, using this V bias up here, where I split the rail. Then it's coming out here, so it's at 1.65 volts, which is half of 3.3, plus or minus the audio signal, which then goes into a low-pass filter. This is the 0 to 20 kilohertz Allen key low-pass filter. It sounds fancy. You just look it all up in a calculator. It's really not rocket science to use these things, but active filters have really great performance, and you don't have to worry about magnetics, anything like that. So yeah, negative 32 dB at 40 kilohertz, and we're able to sample quite fast. We end up actually not sampling so fast just because it's what looks better aesthetically, even though technically we can hear up to 20 kilohertz. Most of the stuff that I think looks good to display from a song is up to like 5 kilohertz, or not even that maybe. Anyways, so at this point we have our amplified signal, and then it's getting low pass filtered, and then it's getting presented to the ADC at this point. ADC 0, you might remember that's what's coming in here straight to the microcontroller. So this is a signal sitting at 1.65 volts, wiggling around there with your AC audio signal, and that's what gets processed by the RP2040. So, okay, next page after that. Miscellaneous. Oh yeah, and just a gigantic LED array. It's so large my computer starts kind of lagging, but all it is all the LEDs daisy chained to each other. And on the right here, it's all the bypass capacitors. So each one needs a little bypass capacitor. So no big deal. I used 0402s. It's very small. You know, the layout was kind of annoying, but it wasn't hard for sure. So now I'll move to the layout. All right, so now we're in the layout. You can see it's a pretty big board. It's about 12 inches across. It's quite large for a PCB, but that's kind of, you know, with this many LEDs of this dimension, it just kind of makes sense to go big. I do want it to be a wall display piece, so that was kind of the point there. You can see the array of LEDs, how they're daisy chained with the little bypass capacitors next to each one. Starting down here to talk about the actual circuitry, you can see these are the power connectors over here. So there's a 100 mil header up at the top that you could use if you're just like messing around on the bench. You want to power it up. There's a barrel jack here, and a word of caution, there's no regulation to step this down to 5 volts if you plug in more, so you have to make sure you're putting in a center positive 5 volt barrel jack if you're going to use this way to power it. But again, you can see how big these tabs are. The mechanical robustness is better than any of the other options. But the USB-C connector, you can see it does have through hole, so it's not so bad. You can, and it's really convenient to be able to use like any old laptop charger, you know, USB-C cable on your desk to power it. So that is what I've been doing. You can see here those two 5.1K resistors hanging off of the communication channel lines to allow it to deliver 3 amps at 5 volts. You can see the differential pair for the USB communication, the data lines which come over here through these two resistors and go into the RP2040 there. So that's how I program it and get print statements off it, stuff like that. This last connector here is the surface mount 3.5mm headphone jack. Surface mount might not have been the best idea here because it is going to sit vertically against a wall, so the weight of the cable will tug on this, but it does have these through-hole mounting pins, so that helps somewhat, even though they're not soldered in. So if we talk about the analog circuitry for a sec, since that's kind of what we're looking at here, you can see the audio jack, the left and right lines coming in through here. You can see a test point here for the right, test point here for the left. So now they're capacitively coupled. These are those resistors that bring it up to half the supply voltage. And this is that analog switch that they're going into. So one of the inputs to the analog switch, it's through these two 1K resistors. Those allow it to kind of sum the two signals here going into the first pin of the analog switch. Going into the other input is the signal from U4, which is the MEMS microphone. You can see it's a really tiny part. That's a really great thing about MEMS microphones compared to condensers or electrets or whatever you call them. You can see it's got its own little bypass cap. It goes through this giant decoupling capacitor. It's like probably as big as the chip. And it goes into the other input in the analog switch. So depending on the signal that the analog switch gets from the microcontroller, it'll allow one of these two analog signals through. It's going to come out and it's going to go to the first half of this op amp, where it's going to be amplified. And the amplification is going to be set by this. This is the digital potentiometer, and it's a 10K digital potentiometer, and we're in an inverting op amp amplifier configuration, so it's 10K. The input resistors are 1K, so the maximum gain you could get is a factor of 10 here, which is more than you would need because both of the signals can go up to about a volt. So we really only need a gain of like 2 or 3 times here. But you can configure this. You can see these 3 lines coming off of it going to the microcontroller. So you can configure the value here for either gain or attenuation. That's the nice thing about using an inverting amplifier rather than a non-inverting. And you can see here, these are those resistors I talked about. So if you were having trouble with this or whatever, if I guess, this is kind of an expensive board and I was doing it for a class, so I was on a pretty fixed timeline. I didn't have time for a Rev 2. So if I had trouble with this, the idea was I could take R25 and R24, which are 0 ohm jumpers. I could remove them, and I could take R34 and stuff it with an 0805 resistor of my choice, and then I can just have it acting as a fixed gain amplifier. In the end, I'm not doing any sort of fancy like automatic gain control in the loop, even though I could, because I'm sensing the signal at the output with the microcontroller that controls the gain. I'm just using a fixed gain. So in the end, now that I know that value, it'd kind of be simpler to just use that. But it's nice to be able to change the gain with software rather than having to desolder and mess with a bunch of different values before I found one I liked. There's a test point for the amplifier output, and after that it's coming over here, and this right here is that Sallen Key low pass filter. As you can see, right, there's really nothing to be scared of with Sallen Key low pass filters. It's just some passives and an op amp, and there's plenty of online tools that'll tell you exactly how to configure them. So it's going through there. There's the filter output, and somewhere I guess on the second, the bottom layer, it's going over to the ADC input of the microcontroller. I guess that brings us to the microcontroller here. There's plenty to say about how you lay out a fine pitch chip like this and how you do the bypassing and all that jazz, but that's not really what this video is about. Maybe I'll make a different video about laying out for the RP2040. What I will talk about, I guess, is you can see here, these are those state LEDs, so it'll light up. When you turn it on, this one will be lit up green, and as you push this toggle button here, toggle mode, it's going to toggle through from 0 to 4. And as I said, I may have mentioned this already, 0 is doing the FFT of the microphone input. So it has the analog switch to listen to the microphone. 1 is Conway's Game of Life. 2 is the FFT of the input from the 3.5mm headphone jack. 3 and 4 are unpopulated, so I'm trying to think of what different things I'd want to display on those. So plenty of possibilities for you if you wanted to copy all this stuff and write your own code to add onto it. It's all going to be on the GitHub link, so you can certainly do that. Here's the serial wire debug. These are the reset and boot buttons. so you don't have to unplug it like on the RP2040, or sorry, the Raspberry Pi Pico, and kind of plug it back in every time you want to reflash it. So this is something I think is worth mentioning. You can see this 100 mil header with 4 pins. I broke out a couple extra ADC lines that you could use for kind of adding functionality to the existing code base that I've written. So these 2 ADC pins, the thing I had in mind in particular was I've got this prototyping section I put over here where you have a bunch of kind of unconnected through-hole soldering points. They're just basically 100 mil perf board and a couple of like buses. So there's a 3.3 volt bus and a ground bus where you could hook up a circuit of your own to the internal voltage domains that I've got going on the board. You could use like one tiny little wire, bring it over to an ADC input, and you could add another sensor that's being used somehow. So the thing I had in mind in particular was like a photodiode or like a photoresistor to see how bright it is in the room. That could feed back to one of these ADC pins, and then you could change the brightness of the LEDs dynamically based on how bright the room is. But I'm sure, you know, there's a lot more stuff you could do with this if you were inclined.
All right, so I've got the board set up here and I have it set to state 0. So this is kind of how it'll wake up if you just power it on. And you can see it's capturing my voice pretty well. And I just wanted to test it a little bit on screen, show you a few different test signals that I can put in so we can see the frequency content. As you can see also, I have the colors kind of fading. So this is something I'll talk about when I do the video about the code, but I have it set in the HSV color space. And there's a periodic interrupt that increments the hue by 1. So it goes, 0 to 360 and then repeats. And the nice thing about the HSV color space is it's a very smooth transition all the way across. So it's you'll see it pan through all the different colors and then kind of cycle back in a very smooth way, which is hard to do if you leave it in the RGB color space. So anyways, what I got set up here, I'm talking of course, and that's what you can see now, but I've also got a speaker here, which I'm just going to put over there. And I'm going to play some test signals and some music and just show how it all looks on the board. So I'll go to a tone generator, and I believe I'm sampling at like 10 kilohertz, but let's see, I'm going to play a 500 hertz tone. Here we go. Now you can notice the side lobes, the kind of like side frequencies going down over time. That's because there's a algorithm going on in the code that keeps track of the highest amplitude that it's perceiving and kind of normalizes the whole spectrum to that so that we're always using the most height in the columns that we can. I'll pause that signal and we'll put like 1 kilohertz. See what, I'm going to turn the volume down a bit too. Here's around, let's see, 1 kilohertz. So you can see we're probably sampling around like 5 kilohertz if this is what 1 kilohertz is showing up at, because right, there's 1. If we go to 2 kilohertz, I'm using an app so I have to like tap through to get exactly 2000 hertz. There we go. Yeah, so we must be sampling it maybe the max frequency we can see is around 2.5 kilohertz. And that sounds quite low, right? People say you can hear between 20 hertz and 20 kilohertz. But I found that looking at that large of a frequency span, most of the stuff that you perceive and you're kind of aware of when you're listening to music is much lower in frequency. So you can kind of see what's happening there, right? Those peaks are growing, 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 because as I don't talk, that's the loudest signal it's seeing, and it's trying to normalize the whole spectrum to that height. So that you can see the noise gets larger, but also the signal does. And I think that's nice, because no matter what volume of music you're listening to, it won't just be like a couple pixels high. It'll take up the majority of the array every time. So now I'll play some songs just to show how that's going to look. So I'm going to show what it looks like when you toggle through the states. Like I said, only states 0, 1, and 2 have any code associated with them right now. 3 and 4 I left blank, and I'm going to, maybe fill it up over time, but honestly maybe not. But certainly you could if you wanted. So if I toggle it by 1, you can see we're doing Conway's Game of Life. There was one kind of fun twist I put on this, which is that one thing that can happen when you're trying to run Conway's Game of Life is you can get stuck in some sort of periodic state where maybe it's like 4 different states and then it repeats, and for whatever number of states it takes to repeat the cycle, you'd have to keep all of those in your memory to check if you're actually stuck in some periodic state. And that seemed kind of annoying, so instead of doing that, what I did is I added a very small probability that a cell which should survive to the next epoch or come alive on the next one will die anyways. So kind of like a bit of randomness inserted. And what that does is if it gets stuck in any sort of loop for that long, one of those cells is going to die. So it does have a thing that checks if a frame has repeated from the last frame, but aside from that, the only way, like right now for instance, the only way it breaks out of cycles that it gets stuck in is by having the statistical likelihood of these things dying. And I thought that was kind of a fun twist. I think it makes it a little bit more... it's fun to add a little bit of randomness to something that's otherwise very deterministic. Anyways, toggle again. This is the state where if there was signal coming in through the audio jack, you can see when I touch it actually, it starts doing stuff. If there was signal coming in through there, and you can see now it's doing that thing where it's trying to auto range, so it's kind of amplifying the noise. So yeah, if you have no signal on it and you're hooked up to the 3.5 millimeter, then you will just kind of get whatever noise is present in the circuit. But if you have any sort of signal coming in through an actual wire, it will cancel this out. It'll be much larger in magnitude than this noise, and you won't see this noise that we're seeing now. As you can toggle through the other two, nothing really happens until you get back to 0, and then you get back to listening to the microphone pick up my voice. So yeah, that's all the states it can run in.